Yesterday in class, we talked about, and I showed you a demonstration where we mixed two solutions together and we produced the result that you see here on screen here. And so we're going to talk more today about how we can represent that type of reaction in a number of different ways. And so let's get right to it here. Now, first off, let's talk about what a molecular reaction is, and a molecular equation. And what a molecular equation is, it's going to be when we have a complete chemical formula of all the reactants and products. So in the demonstration that I showed you yesterday, as we talked about, we mixed together two soluble ionic compounds that were in solution, and we produced one insoluble product and one soluble product. So what we mixed together is we mixed together some lead 2 nitrate, which was aqueous, and we mixed together some potassium iodide, which was also aqueous, and we produced a double replacement reaction where the metals switched places. We practiced and made sure that we rewrote formulas based on charges of ionic compounds. So potassium was a 1 plus and nitrate was a 1 minus. They came together and they were aqueous, and we know they're aqueous because of the solubility rules that we talked about yesterday. Alkali metals are soluble, so are nitrates, so we have definitely a soluble compound there. And then we also formed PbI2, which is lead 2 iodide, which was our solid yellow precipitate that we see up above. That lead 2 iodide right there is all our PbI2, which now has settled down to the bottom of the beaker today. And I'll show you that today in class, or I did show you that today in class. And then we can also balance this equation. And so we have 2 nitrates and 2 potassiums, and there we go. So now we're balanced. Okay, so this would be considered a molecular equation, complete chemical formulas of everybody involved. And so if we're asked to write molecular equations, this is what we do. And oftentimes this is the best way to start off on a chemical reaction. Now, we can also write what is called a complete ionic equation. And this is where we take it and we ionize or dissociate all strong electrolytes. Okay, so we had 3 strong electrolytes in this reaction. We first started with the lead 2 nitrate. Now, if we ionize lead 2 nitrate, so before we mixed the lead 2 nitrate and the potassium iodide together, we had solutions that just had ions floating around in there. So we had the lead ion, and that was aqueous as well. We also had the nitrate ion, also aqueous. We had the potassium ion. We had the iodide ion. Both of these are also aqueous. So all of our ions, and then we had the potassium nitrate. So we had the potassium ion once again, and we had the nitrate ion once again aqueous. Make sure we put a charge on those guys. And then we produced lead 2 iodide, which is not a strong electrolyte. It was actually a solid form. So we're going to keep that together. PbI2 solid. Okay. So that would be considered a complete ionic equation. Okay. We just ionize everybody who's aqueous or is a strong electrolyte, which are going to be aqueous in the same way. Now, there's also the idea of what are called spectator ions, and these are going to be identical forms of ions shown as both reactants and products. Now, the important thing to remember is they must be identical. They must be the same exact charge, and we can't confuse it as if one side has a hydrogen ion and one side has a hydrogen gas, which is diatomic. Those would not be identical forms. They would be completely different forms, and we'd treat them differently. So we're looking for spectator ions, identical forms of ions on both sides. So here's one spectator ion right here. Right here we have a nitrate. There's a nitrate. And over here we have a nitrate. Those are both identical to each other, one on the reactant side, one on the product side. So those would be our spectator ions. So the nitrate is our first spectator ion. And see if you can identify the other spectator ion, and pause the video right now, and then come back and see if you've got it. Well, hopefully you did pause the video and you found out that the other spectator ion was the potassium ion, because the potassium ion is exactly the same on the reactants and the product side. So those are our 2 spectator ions. K1 plus. Okay. Now, when we write what is called a net ionic equation, which is next, a net ionic equation is an equation where we actually write the reaction and we just omit we leave out the spectator ions. And sometimes it's easier just to cross them out. So I'm going to go back up above and cross these guys out. So I'm going to cross out my nitrate because it was a spectator. And I'm going to cross out my potassium because it was also a spectator. Now, I'm going to rewrite this as a net ionic equation. So all I'm going to write are the players that were involved. That was the lead 2 as an aqueous. I get that from right here. I also have my iodide, which is also aqueous. And then I have my solid lead 2 iodide. Oops, that's the solid there. And that is my spectator, or that is my net ionic equation. And we'll have to balance this too. So we have 2 iodides there, and now we're balanced. So this would be considered a net ionic equation with spectator ions crossed out. Okay. Here's something to be aware of. If every ion in a complete ionic equation is a spectator, then we see that there's no reaction occurring. Okay, so if we ionize all the reactants and we ionize all the products and no gases are made or no solids are formed, precipitates are formed, then we don't have a reaction occurring. We just have a group of ions floating around in solution. And we'll see that happen sometimes. Okay, let's take a look at an example. Now, if you would like to pause the video right now and actually do this example yourself and then come back and check, that would be a really good thing. So we have 0.25 molar solutions of calcium chloride and sodium carbonate being mixed. Write the complete molecular equation, including state symbols, is the first thing we want to do. Okay, so I'm going to just annotate this. So we're writing complete molecular equation, and we're definitely going to include state symbols. Okay, so that means we're going to write the entire equation. So first off, let's do calcium chloride, and that is an aqueous solution. And we know it's an aqueous solution because it tells us 2.2 molar solutions. We're going to also have sodium carbonate, also aqueous solution. And now we're going to do a double replacement reaction where we take the metals and rewrite them with nonmetals. So we're going to take the calcium and we're going to put it with a carbonate. And so we're going to get calcium carbonate. And we're also going to get sodium chloride. Okay. Real quickly, I'm just going to balance this guy. So we have 2 chlorines and 2 sodiums and one calcium and 1 carbonate. Okay, now we're balanced. Okay, now we're going to apply solubility rules to see if we have a solid formed here. And we know the solubility rules on sodium chloride. It's got an alkali metal in it, so this is going to be our aqueous. And calcium carbonate. Carbonates are soluble when they're with alkali metals, but not when they're with an alkaline earth metal. So calcium carbonate is going to be our solid precipitate formed. Okay, so we've written our complete balanced equation and we've included all of our state symbols. Good. All right, let's take a look at what we need to do next. We're now going to write a complete ionic equation and we're going to identify spectator ions. Okay, so ionic equation, remember we cross out, we are going to ionize everybody who's a strong electrolyte. So calcium and the chloride ion is definitely ionized. Our sodium plus our carbonate ion. We're going to have calcium carbonate. We are not going to ionize it because it is a solid. And we're also going to ionize the sodium and the chloride. And I'm going to ignore, just for the moment, I'm going to ignore the balancing just for the moment. I'm just going to throw all my aqueous state symbols in there though. Okay, there we go. Now, it did ask us to identify their spectator ion. So remember, spectator ion is an ion that is exactly the same on one side of the equation, on the other side of the equation. So we have sodium, which is exactly the same as sodium here. Those are two spectator, or that's one of our spectator ions. We also have chloride ion listed here and a chloride ion listed there. That's my other spectator ion. Now, we do have calcium as an ion, as a reactant, but over here it has come together to form an ionic compound, so they are not identical. So the calcium and the carbonate are not spectators. They're actually going to be included in our net ionic equation, which we're going to do next. So it asks us to write the net ionic equation. Remember, net ionic equations leave out spectators. So we're going to have a calcium ion, plus we're going to have a carbonate ion, and we're going to form calcium carbonate. And let's double check on our balancing, 1 calcium to 1 calcium, 1 carbonate to 1 carbonate, and we are set and ready to go. If we were to model this, really quickly here, in our beaker after this reaction, let's go after the reaction, we would have, most likely, we'd have some calcium carbonate as a solid formed down here. We would also have some sodium ions and some chloride ions floating around in solution up here, just like that. And if you're interested in the ratios, the ratio is a 1-to-1 ratio of the sodiums to chlorines, because we look back up here at our complete equation, we did have 2 sodiums here to 2 sodiums there, and we also have 2 chlorines here to 2 chlorines there. So it is a 1-to-1 ratio on those sodiums to chlorines, and so that's how we would model it. Okay, that's all we have today on writing molecular equations, net ionic equations, and identifying spectator.